Okay, so let's start with feature detectors. So why do you think you need features? By the way, right, what would be your understanding of a feature?
Distinctive, which we can use to identify particular object.
Yeah, which not just one point, maybe a collection of let's say interest points or things like that, right? So you can think of these as being interest points or something like that, right? So which kind of allows you to allows you to identify certain things in one image, and then maybe you can actually match it across another image, right? And this feature detector thing, right, often arises. So okay, so I think let me start by kind of talking about types of features. So example could be corners. Well, in fact, we could start with lines and edges, right? That's something that we saw earlier. So you can think of lines, corners, blobs. There could be so many things, right, that you can think of as features, and so on. I mean, so etc. And when we talk about features like these, right, these are kind of, these are not image specific. Okay, these are kind of generic in nature. By which I mean that, for example, if you look at how they match fingerprint and all, right, those are very specific kind of features that are kind of unique to fingerprints and so on. Whereas this is not like that, right? Even facial features and all, sometimes when you do face recognition, there are certain things you actually find out, I mean, that helps you recognize people and so on. But this is not like that. So when we are talking about feature detectors, we are talking about something which is much more generic, right? So which should be something that is uniform. Whichever image I pick, I should be able to tell where are the lines, where are the corners, and so on. Okay, so what is the need for these? Yeah. Why do we need them? The need for features, right? So I can list a bunch of things, okay, that where it is useful. So need for features, you could use it for let's say mosaicing is one of the most common things that it is used for, which basically means that you have an image, and then you have let's say, right, multiple images of a scene, and you want to kind of stitch them all together in order to create a panorama, right? So then, I mean, you need to be able to find out what is the, say, relative geometric alignment between these images, so that they can all be aligned properly. Otherwise you can't just put them one next to another. Okay, that won't look good. So you have to align them, and therefore to align them, right, what you need are actually features that you can track across. So you should be able to tell that this feature has gone here, and the same feature has perhaps appeared here, and that way you can kind of keep track of where the feature is. That kind of helps you, and if you have enough number of them, then you can actually do this kind of geometric alignment. Okay, and this mosaicing does not even require depth information. I mean, that's what is nice about it. Okay, it doesn't require you to know the depth of the scene. Without that, right, you can actually do it purely based upon what is called homography, which I think we will talk about in very briefly when we do this one. When we do what do you call this one, geometry. Then there's something called stereo, right, or what is called multi-view stereo. Stereo typically means two view. Multi-view typically means multiple views. And here, right, this might be more from a point of understanding about what is this, a depth of a point, right? Here, like I said, there is no notion of really a depth coming in. You don't really care about that. You just want to be able to align images. Whereas in stereo, right, like I said before, you may have a scene point somewhere, and then right you have a camera, right, which is whose center is here, and then you have another camera, right, whose center is here, and both of them are actually watching this, and you have a plane here, the image plane here, okay, and this point, right, lies here, and when seen through this view, and seen through this viewpoint, right, so you see like that, and if you just see it from one view, which let's say view number 1, and then you've got another which is like view number 2. When you see from view number 1, so this is a 3D point, right, some P point, so let's say it falls here on the image plane, and when you're watching it from elsewhere, right, then maybe it falls here, right, according to this ray, and you have to triangulate to tell where this point is. So if I just give you one view, right, you can of course extend this ray behind, but you don't know where to stop, right, it goes all the way. Correct? I mean, it just goes all the way. So you don't know where to stop. Whereas if you could do triangulation, that means you have another view, and from which, right? But then what would you need then if I had to triangulate? If I had to reach this point, right? What would I need here?
That point on the plane.
Yeah, you need to know a correspondence, right? You need to know that this point is here. Then only this line can be drawn, right? Otherwise, you can't draw it arbitrarily. So you need to know that this point has actually occurred here. And therefore, right, you can actually extend this ray and then see where they meet. I mean, in an ideal situation, they would meet, but given noise and all, they may not actually always intersect, but they'll be very close. And then, based on some least square sense, you can sort of tell where that point is, right? So again, in such cases, you are actually doing a correspondence matching, what's called the feature matching problem. And in all of this, right, there are actually two things which you can see. One is the fact that there is something called a feature, I mean, you need a detector, right? That means you need to be able to flag features in an image. That means somebody gives you an image, you need to tell what are all the interesting features out there. Then you need to be able to match them, right? So suppose I have 2-3 images, I find features here, I find features here, I find features here. But just that is not enough. I need to be able to do one more thing, which is to be able to match them, because unless I match them, right, none of this is very useful. I mean, if I simply get feature points in every image, what do I do with them, right? Except for knowing that that this image has a lot of activity, but then beyond that, I can't make much use of those images. So what you need is a descriptor, right? So in that sense, right, you have a detector, and then you have what is called this one, a descriptor. A descriptor actually defines the feature so that you are able to match, okay, because it should have something that borrows from whatever is around it, and then it should be able to tell that, okay, this is the way this is the way I am, right, at that point. And if I look the same in another point, right, then it's me, right, in the other image, and that's how you have to actually. And of course, you can make use of certain constraints in order to be able to not look all over the image, right, if possible. For example, in stereo and all, right, there are ways to actually restrict the search space and so on, that we will talk about when we do actually geometry. But in general, right, let's just say that we are able to match the features, and then if we can do the matching through a description, through a descriptor feature, this one descriptor, then you can actually do a lot of things, right? And some other things, right, that you can do is, for example, people in fact match different viewpoints. Of course, this is all subsumed in the this is actually subsumed in that, but this I am putting because this has been used. For example, there was a time when people, before deep learning, advent of deep learning, right, there was a lot of work that used to show that given an image taken in the day and then given the same image taken in the night, and from a totally different viewpoint, that you could still match all those features and establish that it's the same scene. I mean, to a reasonable extent, you could say that this perhaps is the same scene that we actually took in the morning. So again, you need to have enough number of matching there. That's when you can say with some confidence that, because photometrically you cannot match them, because this is day, that is night, or different times of the day, right? So you can't simply you can't subtract or something, right? You can't do that. But what you can do is you can match enough number of, if there is enough number of matches that happen, and right, then you can say, right? So this is like day night. Then object recognition. Okay, it can even be applied for, let's say, recognizing an object. which basically means that if you wanted to do some kind of an identification, right, of this one particular object, then maybe you can actually get what is called what would be like like sort of holistic sort of a description of that object, right, based upon the features that you have, and then based upon that you can match. I mean, there is something called HOG, histogram of the grade of oriented gradients. So there are various types of these features. So right, I mean, each one has something that is sort of interesting. And motion estimation. So this is like this again something that is useful. For example, and if you want to track, right, if you want to track a point across frames, right, you have, let's say, a video. Suppose, let's say, right, you have a cricket ball, somebody is bowling, and you have a video, and then suppose you wanted to track that ball, right. So you can actually make use of, again, you need features to be able to track that ball, right, and there you can use something like a temporal consistency and so on, because that between frames there is not going to be much of a movement. That means the ball cannot just suddenly go somewhere else, right. So there is automatically a constraint. So you can have constraints like it cannot have moved too much, it cannot have changed its intensity too much within a window, and you can actually formulate problems around that and be able to come up with features that allow you to track them across frames, right. The main difference between that and the other ones that I showed, the earlier ones, is that earlier ones, right, they don't care about any kind of a temporal consistency. It's like today I take an image, tomorrow I take an image, there is no consistency in terms of the time or anything, right. Just that I have two images and I have to match them. Whereas motion, when you say, right, that's like a video. It's like a continuous activity, right, which you take within a minute or something, and then within that there's a lot of constraint, right. I mean, like I keep saying, right, it's actually it's kind of I mean, if you really sit back and think about it, right, a video has so much information and there's so much consistency there that we don't seem to even be aware of it, right. I mean, you try to play around with the video, insert something that is wrong, do something to it, it will just immediately show up. I mean, it's very difficult to hide something. I mean, it's very difficult to tamper with it and do. Of course, people keep tampering, but I think that all comes out because there is inherently, right, things are so nicely tied up that you can't alter it so easily. Whereas static scenes are relatively easy to play around with. The moment you put a video, right, so there are features that make use of constraints like that, where you sort of impose constraints of the kind that I kind of just now mentioned. That means the motion would be slow across frames, and then the illumination would not have changed so much, and so on. Okay, so the properties of features, right. So I'll write down a few of them. Okay, what is called repeatability. Okay, which actually means that repeatability means that if I do it on one image, next time I attempt it, I mean, it may be a slightly sort of a different image taken under a slightly different condition, but I should be able to get the same feature there, right. So that repeatability is important. Then this one, a distinctiveness, right. I think somebody pointed out. So it should not be something which I mean, it should stand out, right. A distinctiveness is more in terms of, so it should be, right, easy to match. What we mean is by this, it should be easy to match. Then locality. Okay, so normally, right, we expect these features to be kind of local. Okay, we don't like a PCA or something which is more or less a global kind of a feature, right. PCA can also give you features and all. That's more like a kind of a global feature, but most of the time, why do you think that a global feature is not a good idea? What would it? What kind of problems would that run into? Sort of, yes, maybe, yeah, that I agree. What are the problems that you have? Mainly, right, the problems that you have is in terms of what are called occlusions. See, for example, right, if you are seeing a spanner, let's say, right, you want to see a spanner, but let's say something is sitting on top of it, a part of it, right, you don't even see. Then what happens if you are looking at a global feature, right, and you don't know whether it is occluded or not, right. So when you try to pick up a feature from there, right, it won't simply match at all, because part of it is right, you can't even see. So therefore, global features are not actually a good idea. So what would be good is if it in the spanner, right, if you can pick up a lot of local features, and then you say that a major fraction matches. So I have an original spanner which I know has these many features, and then I have this sort of occluded spanner for which also I can get a bunch of features, and I know that and I know and see, so when I match, right, there will only be a certain fraction, but there will be still a certain fraction that will match. And maybe I can say that with some sort of reasonable probability, right, I might say that because so much fraction is matching, I might want to believe that, probably it's that spanner, right. Whereas if I take a global thing, there is no way to tell whether it's that object at all, right, because it simply will not match. Okay, locality, right. So what that means is robust to occlusions, clutter, and so on. Quantity. Right. Quantity means there should be, right, enough of them. I mean, it should not be like, like in an image, if I apply these features, I get only 3 of them or something, right. I should be able to get enough number of them. They should be repeatable, they should stand out, distinctive, they should be locally expressive, and quantity, right. So you should have, enough of them. Right. You should have enough of them so that we are able to do some matching and so on, because many applications require, it's not enough if you have just one feature or something, right. You will need a good number of them, and normally there will be noise, right. When you try to match, there is always going to be some noise in terms of what you are trying to match, and any amount of robustness that you want to bring to that noise will depend upon how many features you have, right. So you can then that will sort of take care of some of the outliers and so on. So you need this. Then accuracy. So by accuracy, what we mean is, okay, it should be a precise localization. Okay, that means the feature, right, you should be able to tell where it is exactly, right. So when you say locality, right, that simply means that that is something which you can actually derive out of a local area, but that doesn't talk anything about how precise you are, right, in terms of telling where that particular feature is, right. So the accuracy in terms of localization, and most of the times it's all about where it is, okay, in the image. The intensities and other things are being used to actually detect, have a description of that feature, but in addition to that, it's also important to know where it is in that image, okay, because that is what will kind of decide a lot of things, geometric information, right. So precise localization, then efficiency. Then efficiency, which is like it should be to the extent possible, it should be something which you can do in a serial time. That means given an image, it should not take a long time. Time efficiency means computationally efficient. Okay, so you should be able to get algorithms that can do it in a relatively small amount of time, right. So all these are, you can add to this list, but then these are all some of the most important things that you would expect of a feature. Now, right, let me just show you a few examples just to give you an idea about what this might look like. So for example, right, so for example, right, when you kind of say talk about object recognition, right, you could have a database of objects. For example, right, you could have a phone, you could have a shoe, you could have this toy, soft toy, and then you can have different features coming out of that, and then you can store them, and then right, you can actually match them. And then right, this is what I mean. So when you want to do recognition under occlusion, right, so the fact that right, that the phone is hidden by the shoe should not hamper the fact that should not hamper your ability to be able to tell that there is a phone and behind the shoe. Okay, so such occlusions are very common. Then you see location recognition, right. So what this means is that, okay, so if you look at the top image and then if you look at the bottom image, they are not exactly taken from the same viewpoint, right, as you can see, because this has more of the left, right, as compared to the one on the top, right. So it's kind of a different viewpoint, but then all these things that you're seeing out there should stand out in terms of being features, right, that you can actually pick up and match across images, and so location recognition means, like I said, right, be it day or be it night, be it this viewpoint or that viewpoint, you should still be able to tell that I'm probably looking at the same scene. Then this you can use for what is called you can also use such features which you'll see later to even tell where the camera is and so on. Then you can do image matching. This is somewhat similar to what we saw earlier. So for example, right, even though the viewpoints are so very far away, right, quite far away between the two, but then you still should be able to, for example, like this one, look at the shape it takes there in the other image, but you still want to be able to match them. You want features that could, and look at this, right, this is the NASA Mars rover image, and if we as a human, right, if I ask you where are the points that you can match, doesn't look like an easy job at all, right? It actually looks like these are two completely different scenes, but actually, right, it's not the case. Apparently, right, this bunch of points and this bunch of points are actually the same. Okay, it's not right. Visually, when you see it the first time, it looks like you're looking at a different terrain altogether. So you can see that, right? So you can see that there are so many situations, where you need features of this kind, okay, and which will help you do these kinds of tasks. Now there is something, right, that so there is some invariance, okay, that we actually expect out of features. There is something called invariance and there is something called a covariance, not the covariance that we talk about in statistics, okay. These are covariant and invariant, right. So so I think these are the two things that we use. So what we actually believe, see, changes in an image can occur due to actually two primary things. What could be those? In an image, right, if you compare two images, something is not the same. What could be those two things that actually makes the appearance of an image to be this one different? Huh? Okay, so one is what is called photometric information, right. So photometric information, and what is the other? Other could be geometry, right, because of viewpoint, right. You can have the same lighting, but then I take the image from another viewpoint, so that again makes it look doesn't, so the images don't look identical. So you have got what is called what you can call as geometric. So you have variations primarily, right? Primarily, I mean, you can kind of think of changes occurring in an image because of photometry, which is illumination, or geometry, which is typically based upon the viewpoint. Okay. Now you want a feature. Okay. So when you say that I want to be able to build features, so what you would like is you would want your features to be, let me say, dash with respect to photometric changes. Invariant, right, because so that if there is a slight change in intensity or if there is a sudden illumination, extra illumination, still want to be able to say that it is the same feature, right, invariant. And features to be with respect to, okay, now I think you can actually guess what might be the other answer, because there are only two of them. What would that mean if I write covariant? What would that mean? Yeah, they both should change the same way. For example, at a corner, right, if you had a corner somewhere in an image, and suppose I did a rotation of that image, then the corner should also rotate. If I translate, the corner should also translate, right. Covariant means it's like saying that something like this, right. If I had phi on some f, okay, and if I had f, right, that's my feature, right, f is my, let's say, image. What you're saying is if I do phi of r of f, that means r, I mean, by which I mean some kind of a geometric transformation, or you can call it g of f, then I want this to be the same as r of phi of f, right. So that is a covariant property. Okay, that's what you are asking, and it makes sense, no? I mean, if you scale an image, right, then again, I mean, right, depending upon the scales, see, finally, right, see, when you want to see, this is different from doing the matching. See, when you want to match, okay, you want a descriptor that should probably be, right, invariant to all of this. A descriptor is not the same as a feature. A feature is something that you want to track, right. I mean, if you actually rotate the image, then it should have also gone the same way, so that I know that a rotation happened. Otherwise how would I know that actually a rotation happened, right. So this covariant feature has to do with the fact that if I kind of get that feature, and if I've rotated that image itself, then rotated whatever you did, some geometric, it could be affine, whatever it is that you do, then that same transformation should then get applied on the feature, so that is what will tell me information about what has happened between the two images, right. But then the thing is, when I match those two images, that matching when I do, right, at that time, the sensitivity to illumination and sensitivity to geometry and all should not be there, because the underlying description should be independent of that. I mean, otherwise, if that becomes sensitive to all of them, then I cannot ever match, right. So that description part we will come to later. This is okay, Rohit. I think you look a little okay with that. Okay. Huh.
The quantity part I'm not able to.
Which one?
Quantity.
A quantity means enough number of them. That means, right, given an image, I mean, if you say that I can only get you one feature, right, I have a feature, this one, I have an algorithm to find a feature, but that feature is so sparse that I can get only say 2 of them in an image. What do I do with them? I should have enough number of them, right? They should be distinctive, there should be enough number of them, because most of the times it's not enough if you just have one correspondence and all. You actually need multiple number of them. That's what I mean by enough. So, enough number of them, I say enough of them means enough number of them. There should be enough number of them. Okay. Now, there are various now there are several types of FDs, feature detectors, and the first one, right, that I thought I will talk about is actually a corner detector. Okay.